that was some of the motivation. You know, you see this sometimes when they're doing the surveys, and they've got the one guy with some guys just suckers just standing there with like a pole. You know what I mean? And then the other guy is over there with the tripod and the thing. He's going there and he's jotting stuff down, or probably nowadays he's got the tablet and he's recording all the stuff. Okay. Anyway, there was one of our famous presidents that was a surveyor. Anybody know? He may have been. I don't know. He was a community organizer, so he probably went surveyed, but by that time, everybody asking questions. George Washington, he was a surveyor. He'd go out and kind of see how things are. What's interesting about this is that, okay, you might be like, all right, well, that's, you know, a couple hundred years ago, well, like 400 years ago. Why do we still need this? Well, we still are doing some surveying now, but as it turns out, three-dimensional graphics, okay, like on the computer, at the lowest level are triangles. Okay. In fact, so any movie that you watch that has computer graphics, not even if it's a live-action movie, even if it's like one of the Marvel superhero movies, something like that, and they've got, you know, the special effects, they've got something like, you know, around, you know, I mean, it's not an actual prop, like if it's all CGI type stuff, or if you're thinking about movies like Toy Story or Shrek or whatever modern movies y'all are gonna watch now, with yeah, sure, Up. That's still like a decade old. But anyway, at the smallest level, if you were to zoom in on those things, they're not curved. They're triangles. Okay? And for those of you that are kind of into gaming and stuff like that, one of the ways that your GPU, graphics processing unit, or your graphics card is measured is by how many triangles it can process a second. Okay? Everything is triangles. I'm not kidding, people. Everything is triangles. When we deal with sines and cosines and we deal with those graphs, that's how we deal with radio waves and frequencies and cell phones and Wi-Fi signals and stuff like that. I mean, it's amazing, the triangle, that 3 and oneness sort of shape is just, it's unbelievable. Yes, John?
So that could be like, say like you're playing like a classical Mario game. When it's pixelated, it's actually triangle.
When you say classic Mario game, are you talking like Super Mario Brothers, where he's moving, it's a side scroller?
Like,
or are you talking about like Super Mario 64, which is a 3D world which you're running around in? Which one?
Super Mario Bros.
Okay, so that's more of like a 2D type situation, and that is not so much the triangles. I'm talking more about the 3D environments, okay? Because it deals with lighting and the surface and pixelating is a different phenomenon, okay? Not necessarily related to what I'm talking about. Other question? All right. So we're going to draw a couple of large triangles on our paper. So here we go. Hope you didn't draw that. If you did, that's unfortunate. All right. So here's our triangle. Trying to make it not equilateral or not isosceles.
Oh, perfect.
Okay. We definitely want a scalene triangle here. That means no sides are the same. All right. Across from big A, I'm going to have little a. Across from big B, I'm going to have little b. And across from C, I'm going to have little c. And I'm going to drop down a height which is perpendicular to angle B. And just to be clear, that little b is that entire side right there. I'm going to just sort of do some stuff that it's going to appear really unmotivated, like I don't have any real reason to, except maybe I was just kind of bored and thinking about triangles and drawing stuff. And then eventually, after drawing enough pictures, I find out with a pretty cool little like pattern here. And that's, so just bear with me as we kind of explore together here. And eventually we'll get to this thing called the law of sines. So let's talk about the sine of angle A. Going way back 5 weeks ago, 6, 7 maybe weeks ago, when we had a right triangle trigonometry, okay? Sine of A was the opposite over the hypotenuse. So looking at this triangle right here, the opposite is represented by what letter? What's that?
Opposite of
No, I'm sorry, I'm looking at the right triangle here.
So
H, yes. And the hypotenuse?
C.
Little c, that's right.
Little c.
Okay, separate idea over here. Sine of big angle C. I'm now focusing in on this right triangle over here.
Oh, snap.
Okay, so sine of angle C, opposite over hypotenuse. The opposite is H, and the hypotenuse is A.
Whoa.
I'm going to solve this equation over here for H. So multiply both sides by C. So C times the sine of angle A equals H. Over here I'm going to multiply both sides by little a, so I have A times the sine of angle C is equal to H. Multiply both sides by A so that it cancels the A out.
Oh, okay.
So multiply by A cancels A, multiply by A, and still stuck around.
C equals this one.
Now you can see that this is equal to H and that is equal to H, and so therefore this is equal to that by the transitive property of this and that. So we have C sine A equals A sine C. Has a little bit of rhythm to it. C sine A equals A sine C. At this point, I'm then going to divide both sides by A. So this divided by A, and this divided by A. And at the same time, divide both sides by C. So this divided by C, and this divided by C. So that the A's cancel on the right-hand side, the C's cancel on the left-hand side, and I end up with this interesting situation. Sine A over little a equals sine C over little c.
Why wouldn't the other A's cancel out?
Because it's a big game. Yeah.
Because it's a big and a little, that's correct. And because this A is actually wrapped up inside a sign blanket.
Mm-hmm.
And you can't cancel them out if it's wrapped inside of a sign blanket. Alright? Okay. Let us draw the exact same triangle over here, only slightly different. That's too different. I want the outside to look the same. So A, B, and C. And so I've got little a, little b, and little c. But I'm now going to draw H in a different location. H is going to be the distance from vertex A to side little a. Yep. H is really what we call, it's a placeholder. It's a dummy variable in this case. It's a tool, it's a pawn. It's just something that we're using to get to somewhere else. It's the means to the end, and Nick, you can just put that in your pocket over here. Thanks. So, over here now, I'm going to be focusing in on this top right triangle, okay? So, this guy right here, the right triangle here. And let's think about the sine of angle B. So sine of angle B in our right triangle trig would be the opposite, which is H, over the hypotenuse, which is little c. And over here now I'm going to focus in on this right triangle. There's a right angle up here and the hypotenuse down here. So if I say the sine of angle C, okay, you can see this right triangle from here. Opposite, which is H, over the hypotenuse, anybody? Little b. Just like I did over there, I'm going to multiply both sides of this equation by C. So I have C times the sine of B equals H. And on this one over here, I'm going to multiply both sides by B. So I have B times the sine of C So I have this equals h, that equals h, therefore they do equal each other. This equals that. So C sine B equals B sine C. Probably see where we're going with all this. I shall now divide both sides of the equation by C as well as B. So that the C's cancel on the left, B's cancel on the right, and we have the sine of B over little b equals the sine of C over little c. Now if you notice, I have sine A over A equals sine C over C. And here I have sine B over B equals sine C over C. So I can also say that this equals the sine A over little a.
Oh my gosh, they all equal each other.
They do all equal each other.
Oh,
Behold
nice.
the law of sines.
Wow.
Nice.
So over here we will summarize it in a nice diagram and equation. Little a, little b, little c. And we'll say sine A over little a equals sine B over little b, which equals sine C over little c. This is a great example of something that is pretty simple to look at and to understand. I mean I can understand these formulas. There's something over. It's just the sine of that angle divided by the length of the opposite side. Okay, but it's not obvious how to go straight from here to here. You have to do some other stuff to get there. But once you see that other stuff, it's pretty straightforward. Something else to note that's probably a little bit more important, and that is, what type of a triangle does this address? A scalene, okay. Let me put it this way. Does it have to be a right triangle? I mean, this large triangle is ABC. Was that a right triangle? Did I say you have to draw a right triangle? No. Okay. Could it be a right triangle? Sure. But the law of sines is going to work for every triangle. Except for the ones that it doesn't, and I'll tell you about those next week. Okay? But for right now, and the problems I'm going to give you right now, it works for every triangle. It only doesn't work for one triangle.
Which triangle?
The ambiguous case of the law of sines.
Oh wow.
Okay?
That sounds
All right? That's for next week. So that is next week.
Yeah, it does.
Yeah, I'll write it one time. So anyway, yeah, it works everywhere, except for when it doesn't, but we'll worry about that next week. Okay. Let's do some problems. Let's do lots. So, yes, no, last year? Maybe so?
No, I thought
No
we
from
did,
y'all?
but-
What about y'all ladies? No? No? John?
I probably heard of it.
Okay. This might be something that you would want to add to your trig chart. I don't think it's on your trig chart. Also, sometimes when I see people write the law of sines, they have the reciprocal of everything, and who cares, right? No big deal. It's like they'll have little a over sine A equals little b over sine b equals little c over sine c.
Oh.
Yeah, that's the same. 1/2 equals 2/4, just the same way that 2 over 1 equals 4 over 2. You can, it doesn't matter, it's all the same stuff. Okay, let's do some law of sines problems.
Oh, I remember this. I did this.
Okay.
No, I remember.
All right, you'll need a calculator if you don't already have one. So here we go. Consider triangle ABC like the one below. Suppose that B, I'm going to put these numbers on here.
Oh yeah, we did geometry.
B is 58, check. A is 20, check.
You have to solve for like
B is 117 degrees. Solve the triangle. What the heck does that mean?
We
That
have
means-
different problems.
Yeah.
Oh, you
Ours
do?
is different.
I was like,
Yeah,
what?
I was like, do I have the font?
I was looking at everybody's paper.
Oh man, that is you do.
Oh, man.
Oh, this is law of signs, ambiguous case. Sorry about that.
Oh, shoot.
See? Ambiguous case.
I was in my mind.
I wondered why I was an obtuse angle. All right, y'all start labeling your problem and start working through that while I figure out what's going on.
Yeah, we did this last year in geometry. Yeah, I remember having the.
That's really better reading. All right, angle A, 26 degrees. C, 42 degrees. A. All right, here we go. This looks a little bit better, doesn't it?
Yeah, sure does.
Okay, solve the triangle. That means find all the missing angles and all the missing sides. Okay,
Oh, I remember doing that.
no big deal. I'm gonna do the easy thing first. I'm gonna find the measure of angle B. So B is just gonna be 180 minus 42 plus 26. Right? Because all three angles in the triangle have to add up to 180. So I await your answer. Okay. B or C, let's go alphabetical. Let's figure out what B is. Okay? So I can say the sine of angle B over little b equals the sine of angle A over little a. I could also say equals the sine of angle C over little c, but I really don't need all three I don't need a triple equation. I just need two. So this is the one that I don't know, and I have information on little a, so that's why I'm choosing that one here. Okay? I would recommend at this point that we solve everything algebraically, so that then we can just type everything into our calculator all in one shot at the very end. Okay? So we're looking for little b. What I'm going to do is, y'all like to do cross multiply stuff? Sure, let's cross multiply. So b sine A equals A sine B. If I want to get B all by itself, I would divide both sides by sine A. So B equals A times the sine of B divided by the sine of angle A. So I divided by sine A, divided by sine A. I'm not going to always write all the divided by on both sides because unless absolutely necessary. So at this point, I'll just plug in the numbers. Little a is 50. Angle B is 112. And A is 26. Make sure your calculator is in degree mode. Those calculus students tend to put it back in radian. And let me know when you have a final answer there for little b. That's what it says on the back, so your calculator says. I hear 105.8. It's not degrees because it's a length. Now it doesn't really say 105.8. It says 105 point
75.
blah 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 blah, right?
Yes.
Okay. So this is a rounded value. Okay. So it's got a little bit of error because we chopped off some of the end or we rounded up or whatever. Okay. Therefore, we do not want to use this value in our next set of equations because then that error, that rounding stuff, is going to get multiplied and yeah, it's going to extend. So when I'm looking here for little c, I'm not going to use any information about angle B and like the sine of B or little b. I'm going to stick with what the original one was given to me, sine A over little a. So I can say sine C over little c equals sine A over little a. Does that make sense to everybody? Why we're not using the information on B? Okay. So we'll cross multiply C times the sine of A equals A times the sine of C. It looks really familiar here. C equals A sine C divided by sine A. And so therefore C is going to equal, we'll just plug in those numbers. A, which is 50, sine of 42 divided by sine of 26. Enter. You do it all in one shot, and I'm in radian mode. 76.3. Wait a second. Couldn't we just have done Pythagorean theorem on this?
I was thinking that, but isn't that
You are correct.
okay?
Yes.
I was
It
about to
is-
be like, yes, we could.
We can't do Pythagorean theorem. That's only for right triangles. So multiply here. 112, 105, and 76.3. Okay? All right. As a table, see if you can attack number 2 there. When you get that problem number 2, call me over. Are you on the reader? Okay.
I don't know if there's really a need to do that. I kind of remember this from last semester. Right?
Either way you finish. Alright. In all honesty, it looks like the rest of those problems are pretty much the same as those first 2. So I'll tell you what, after you finish problem number 2, call me over. We'll make sure that you understand everything, and then you can work on something else. Today we talked about law of sines. It's a great law.